Okay, so today we're going to jump back a little bit and do a little prerequisite knowledge before we move on to 15.3. So if you are watching this, well, hopefully you're watching this after you've done our 15.1, but you might be watching this after we've done 15.2 or before if you're trying to get ahead in the future. But what we did in 15.1 was we talked about vector fields and how a gradient vector could define kind of a vector field using each point in the vector field and plotting a vector at it. If you've done this after we did 15.2, doing curl and divergence, which is what today is about, is important because we did line integrals last time, and we will need both curl and divergence and line integrals to talk about Green's theorem and Stokes' theorem later. So we're going to combine these two things a little bit later. But let's talk about the prerequisite knowledge we need for 15.3, which is independence of path and conservative vector fields. So most important thing to start with is kind of this definition. So we have some kind of vector field here, F, 3 components, a linear combination of I, J, and K, and there are 2 important fields we need to know about. First, the curl of F. This is a vector field, and so if you can remember that it is a vector field, you'll note that we will use cross product to calculate the curl of F. And I apologize for my handwriting. It's been a while since we've written anything down. Welcome back from winter break. So remember that when we take the cross product of 2 vectors, we end up with a vector. So that will kind of help you think about curl being using the cross product in its definition. The second field we want to know about is the divergence of F. And this will use the dot product. And remember that the result of a dot product is a scalar. So that will kind of help us remember that definition there. First, we will do curl. So we're given some vector field, again, still dealing with the same F general vector field, but the partial derivatives of the 3 components, P, Q, and R, all have to exist. Then we can say that the curl, which I'll get to the practical meaning of it in a few minutes, the curl of F is defined by this cross product. Now this might not look like a cross product, but you'll notice that it is just like we did before with cross products. It's a linear combination, I, J, K, and then you are subtracting 2 components to find the coefficient of the I component. You could also think about it, I think this is a much easier way to define it, as this del function cross the vector field F, which we've had here. So one thing you should note, I gotta write better so that you can see this, note, okay, this del function we are defining to be a vector itself, and it is the operations, each component is the partial derivative with respect to a different variable, kind of in the x, y, z positions. Again, this is probably key for your toolbox here. We want to put this as a definition. So notice that in order to compute the first component, the component that goes next to I, I'm going to do the partial derivative with respect to y of the r component minus the partial derivative with respect to z of the q component. Partial r, partial y minus partial q, partial z. Okay, and we'll keep going just with our usual cross product operation. So let's do one example together. Okay. Yeah. Okay, so I want to find the curl of this vector field if this vector field is defined with this vector. Note that if I plugged in different points, x, y, z, I would get different vectors at each of these points. That's what it means to be a vector field. So, by definition, the curl of this vector field F is given by the matrix IJ, okay? Okay, and then in the second column, it's going to be all the partial operations. And then in the third row, I think it's a column, but these are all rows, I need to enter each of these components. So I'm going to be a little cramped here, but in the first entry, it should be x cubed y squared z. In the second entry, it should be x squared z. The third entry should be x squared y. So check to make sure you've got that too if you can't see this as clearly. All right, so then we just start by doing the cross product. So the first component goes with I. So I only take the partial derivative of this right here with respect to y. That is x squared. Then I will subtract the partial derivative of this with respect to z, which is also x squared. So that will be nice to compute later. Remember, when we're taking a cross product, we have to subtract the middle component. So subtract the j component. And then I go across here. So I will need to take the partial derivative with respect to x of this component, which will be 2xy. And then subtract the partial derivative with respect to z of this component, which would be x cubed y squared. Finally, we get to add on k. Okay, partial derivative with respect to x of this component, which is 2xz, minus partial derivative with respect to y of this component. So 2x cubed yz. Okay. Now, none of these are nicely combinable like terms. I guess we maybe could factor some things out of each component, but I'm just going to subtract these two and write it in vector form instead, just so you can see it. So the first component of this vector would be 0. Then x cubed y squared minus 2xy. And if you're wondering why those two switched, I just distributed this negative into here. And then 2xz minus 2x cubed yz. Okay, and we'll talk about what that vector means, because it means something different at each point in the vector field of F. We'll talk about that in a minute. But first I want to show you this theorem. Okay, so let me move something really quick. E. Gosh dang it, I did not clear enough workspace, clearly. All right, here we go. Okay, so if f is a function of three variables, continuous second order partial derivatives, then the curl of the gradient of f is equal to 0. Okay, so we'll do a tiny proof here. Okay, already set up for us. Note that the gradient, the reason this is important, that the gradient of f these are already derivatives. Remember that the gradient vector is represented by the partial derivative of f with respect to x, y, and z of each of the components. Okay, or f being little f, a function, excuse me, not a vector itself. Okay, so same as before, we're just taking the cross product of some of these vectors. So I component will be partial f. Let's actually write this the other way. I'm going to write them just separately. So partial with respect to y of partial f partial z minus partial with respect to z of df dy, which looks awfully similar, which is important. Okay, subtract the j component. And as you go through this, you should notice that each time, even though it's in a different order, you are getting the same partial derivatives. Okay, let me just add on k down here. Last one. Okay. All right. So why would this be? Remember, our goal is to show that this is equal to 0. It's important we think about some of the theorems we learned earlier. This has continuous second order partial derivatives. If that is true, that they are continuous, that the function itself is continuous at a certain point, then the partial derivatives are equal to each other. So since f has continuous second order partial derivatives, abbreviate. This means in shorthand that fxy equals fyx. And similarly, fxz equals fcx. And fyz equals fzy. Therefore, the curl, this whole thing up here, curl of the gradient vector of the function f is equal to 0. Okay, which is nice. But this has a nice corollary that goes with it. Important. Let me move this back down. Because we define a conservative vector field is one for which that vector field is represented by the gradient of some function f, then if f, a vector field, is conservative, then automatically the curl equals 0. Okay? Also, if it's a vector field, and I can prove that the curl of the vector field is 0, then it has to be a conservative vector field. So really what we need, what I want you to take away from this is that theorem. Okay? This corollary is based on a definition that we're reviewing right now, but these say basically the same thing. It goes in either order. So what you want to note to yourself is we can use the fact that the curl of a vector field f is equal to 0 to prove that that vector field is conservative. Okay? Additionally, that means you can prove excuse me, this right here. And maybe if I want to go back and I want to find f, as they're going to ask me here, this function f, remember that the gradient is just the partial derivatives, so I could just integrate each component with respect to the partial derivative I took, and then I could find that original function f. So that's actually what we're going to do here. So first I want to prove that it is conservative. And then if it is conservative, we need to find that function f. Okay? So first, show it's conservative. That means we want to show that the curl is equal to 0. So make a note to yourself, show curl vector field f equals 0. Okay, so I've got, set this up. That looks like an O. It's gonna bother me. E. It's really hard to write with these things. It's hard to write because I want you to see at the same time, but I clearly can't. I need to figure out a better way of writing. Okay, so curl of f will be I, j, k. Partial with respect to x, partial with respect to y, partial with respect to z. Okay, and then each component goes in the bottom. So yz, xz, xy. Taking cross product, which at this point in the semester I hope you are really, really good at. Excuse me. Okay, so in the ith component, if I want to take the partial with respect to y, I get x. With respect to z, I also get x. So great, off to a good start, already got 0. Okay, across, I will get y minus y. Good, almost there. Kth component, I will get z minus z, which is in fact 0. So therefore, the vector field f is conservative. Smiley face. Okay, so since it's conservative, we then want to find f, the function for which the gradient vector of that function is equal to this big F vector field. Okay, we can do that by looking at each component individually. Remember that since we just proved and equals gradient F, okay, since we proved this, that means that each component here, this is the partial derivative of little f with respect to x. This is the partial derivative of little f with respect to y. This is the partial derivative of little f with respect to z. So I can integrate each of them separately, and that will give me kind of a function I can compare and contrast, look at. Okay, so let's just deal with the x component first. So I will integrate yz with respect to x, and I will get xyz plus c. Remember, going back to plus c now, because this is a function. Okay, so don't forget it. All right, well, that's a good start. Let's try the second component, xz with respect to y. And I will also get xyz plus c. And let's just check to make sure that the z component isn't missing anything. we haven't already covered integrating xy with respect to z, I will get xyz plus c. So therefore, this function f of x, y, and z is the function xyz plus constant c. Okay, and that's it. I'm going to leave example 3 for you guys to try on your own, but it'll be in the field notes for yourself. I know I'm already at 15 minutes, so I want to make sure I get to the next kind of thing. So here's where I want to just have a little paragraph, a couple diagrams on what curl is about. So what else can this be used for? What does it really mean? So the reason the name curl is that the curl vector is associated with how fluid is rotating in a space. Notice that curl is this vector here, and this is the curl at this point here. The vector resulting from curl is this vector here. It's not one of these like tangential vectors pointing in a direction. So particles near this point right here rotate about this axis. Okay, the length of this vector is just how quickly they would move around the axis. Okay, so and then if the curl is equal to 0, we call this irrotational. No, nothing is moving. Okay. All right, and here you can think about it kind of being like a paddle wheel. This would be the vector represented by the curl, and these would be, you kind of like push or pull in either direction for this. So I want you to note one thing. Okay. Rotate about the axis that points in the direction of this curl. Okay, the axis points in the direction of curl because curl is a vector. Okay, how do you know which way the particles are turning? There we go. Okay, let's go ahead and flip to the next page. It's according to the right-hand rule because I guess, you know, everything is according to the right-hand rule. So if curl is less than 0, okay, be clockwise, and it's greater than 0 counterclockwise. Okay, so you can think about using your right-hand rule to point you in the right direction. But I want to move on to divergence so we can see the formula for calculating that. So this is a scalar field. Remember that a scalar field is a dot product. Okay, so again, definition, if we have some vector field, PQR, and all the partial derivatives exist, then the divergence of F is, it can be a function also. Note that it doesn't have to, if we're dealing with finding the formula for the divergence over the whole field, we're not plugging in we're not plugging in x, y, or z, so we could get a function itself before we plug in x, y, and z. But this is, it looks like just the sum of all the partial derivatives of each component, or sum of the partial derivative of each component of f. You can also think about it this way. Remember that this del vector here, is the vector partial x. Sorry, these look like 2's. I know you guys talked about that in class a lot. Partial y, partial z. Okay, but it's dotted with f. Okay. All right, so let's do one example together, and then we'll sum up by talking about what this kind of means in terms of flux or flow. Okay, so if I want to find the divergence at a certain point, so I will get some kind of constant here as my final answer. Remember to think about that when you're test taking. What should my final answer look like? Should it be a function? Should it be a vector? Should it be just a number? Kind of thing. Okay. And I've got this vector field here. This is the same vector field we just did, pretty sure. Or not the one we just did, but the one we initially did for curl. Yes, we did. Cool. All right, so first setup. So divergence of this vector field F. Okay. Well, I'm going to take the partial derivative with respect to x of this first component. And remember, I'm not putting brackets, the fun vector brackets, because it's not a vector. I'm doing the dot product. It's the partial derivative of the first component with respect to x. So that's going to be 3x squared y squared z. Okay. Partial derivative of the second component with respect to y, which is nothing, because there's no y's here. And finally, the partial derivative of the third component with respect to z. No z's here, so also 0. So the overall formula for divergence over this whole vector field is 3x squared y squared z. And the divergence of the vector field F at the point 2, 1, negative 1 is 3 times 4 times 1 times negative 1. Okay, so I'm getting negative 12. Okay, notice there are a couple diagrams over here. If the divergence at F is greater than 0, that means that fluid is diverging from that point. It is spreading out. If the divergence is less than 0, then fluid is flowing to that point, kind of like a drain, or we call it like a sink, well, a drain in a sink. Okay. If the divergence is equal to 0, that means fluid is just kind of flowing past that point. It's not attracted to or repelled from that point. We're just going across like nothing is happening. So, one more theorem for you. Okay, so let me just note that this is connected to this diagram here. All right, so if the vector field P, Q, and R have second order partial derivatives, then the divergence of the vector that represents the curl of F should be equal to 0. Okay, fun theorem for you. All right, and again, name divergence can be understood in context of fluid flow. Okay, then this is the part you want, that the divergence on this vector field represents the net rate of change with respect to time of a mass of fluid or gas flowing from the point per unit of volume. Okay, shortly, divergence measures the tendency of the fluid to diverge from the point. So it doesn't want to go to the point, doesn't want to go away from the point. And we're not dealing with the like kind of why in this class, but just to help you kind of put it in context with another class maybe. This last page has a couple of examples on it. You will not be expected to be able to judge kind of a vector field like this for yourself on the test or on the final, but I have filled these in on the filled notes, so if you would like to take a crack at it, that's fine. I do want to give you one hint. So you can ignore part B, so let's cross that out. Okay, ignore part B, but in part A, I want you to think about the fact that the divergence formula is partial P with respect to X plus partial Q with respect to Y plus partial Z, no R, with respect to Z. Since all of these are in 2 dimensions, that means that there is no third component to this. So that means the partial R with respect to Z is nothing, because they're all in 2 dimensions. Okay, so you can think about that when you're looking at it. I want you to also look, if you were going to do this, look only like at the point or around the point. What's happening as you increase X, what's happening as you increase Y, is it changing, what's going on? Okay, all right, that is our definition of the formulas for divergence and curl.